Okay, so we will get started. Uh, Again, before starting, does anyone have any specific doubts related to any topic? No specific doubts, is it? Okay, cool. So uh, we will start with PCA and then we will move on to kernel PCA and then we will discuss some estimation techniques. I think the popular ones are maximum likelihood estimation and Bayesian estimation. Then we will look at Gaussian mixture models and how to apply the EM algorithm to Gaussian mixture models. Okay. So starting with PCA, PCA has PCA has oops, hey, thanks. Yeah. All right. So what I was saying is that uh, we will go along these lines: PCA, kernel PCA, then estimation, and under estimation we will discuss maximum likelihood and Bayesian, and then we'll discuss Gaussian mixture models and how the EM algorithm is applied to Gaussian mixture models. Okay. Before starting, does anyone have any specific doubts? I'm asking one more. Anyone? Any specific doubts? No, right? Okay. So we will start with PCA. So before starting with PCA, there are a few important things that you should know. Okay, I will call this the prerequisites for PCA. Okay, so what are the prerequisites? The first prerequisite is that go ahead. Yeah. Complexity. What is the complexity? Oh, I see. So yeah. All right. So there are there is one primary issue with PCA. The primary issue is that it captures only uh, the correlation or the linear relation. So it captures only linear relations, which means that if you if you have a data set which looks probably something like this, then it will not be able to capture this particular curved relation. Okay, now it turns out that if you project it onto a bigger space, and if you project it in a clever manner, you can do it in such a way that in the bigger space this curve becomes linear. So this curve can be made linear in a bigger space. But what is the problem of taking it to a bigger space? The problem is that uh, instead of a small dimension d, you will move to a bigger dimension capital D. And in capital D, if you want to, let's say, compute the covariance matrix, or if you want to do any sort of comparison, if you want to compute distance between two vectors, all of them becomes even more costly than doing it in small d. For example, if you have two vectors in small d, x and y, and if you want to compute the distance between x and y, right? So what do you have to do? You have to do d subtractions, and then you have to do d squarings, and then d additions. And at the same time, if you move to a bigger dimension, let me call it x prime and y prime in R capital D, then you have to do capital D subtractions, capital D squarings and capital D additions. In a sense, you are essentially doing a larger number of operations uh, because you move from a smaller space to a bigger space. And why did you move in the first place? You moved because in the smaller space, the relation is non-linear, and you moved it so that in the bigger space it is linear, and so that you can apply PCA. Is the idea clear? And these are the reasons why we start with kernel PCA. Notion is clear? Because capital D is bigger than D, right? So all of the operations become bigger. All right. Okay, so we will continue with the prerequisites for PCA. One is that you should know that the covariance matrix of any data set of, let's say, X, which is given by X1, X2 to X capital N, where X1 is the first data point, X2 is the second data point, Xn is the last data point, and all of them are arranged as columns. So we have a big matrix whose dimensions are D cross capital N. So the covariance matrix of this data set is given by C equal to 1 by N times XC times XC transpose. Okay, now what is XC? What is XC? XC is, instead of X1, I'll do X1 minus X bar. Instead of X2, I'll do X2 minus X bar, and so on. And finally, instead of X capital N, I'll do Xn minus X bar. This is XC. It is also called the centered data matrix. Centered data matrix. Okay. This is the first thing that you have to know. Secondly, what can you say about the eigenvalues and eigenvectors? I'll write evals and evex in short of this matrix C. Okay. First of all of them are non-zero. All eigenvalues are bigger than or equal to 0. Not non-zero, non-negative. Okay. It can be 0. Secondly, one more important point is that the non-zero eigenvalues, non-zero evals of XX transpose and X transpose X, they are always the same. Okay. Every time the non-zero eigenvalues of any matrix, let me change it and write it as any matrix A transpose and A transpose A. Okay. A transpose and A transpose A. They are always the same. Third point is that if you take the trace of any matrix A, it is nothing but the sum of eigenvalues of A. And similarly, if you take the determinant of any matrix A, it is the product of eigenvalues. Product of eigenvalues of A. Okay. One more thing is that trace has a very beautiful property. Trace of any two matrix AB will be same as trace of BA, provided you can multiply AB and BA. Okay, if the multiplication is not possible, then this doesn't hold. But if the multiplication is possible, then this holds every time. Similarly, it is not only for two matrices, even for three matrices, trace of ABC will be same as trace of BCA, and that is same as trace of CAB. Okay. Observe the cyclic nature here. Okay. I'm pulling A from the front to the last, and then B from the front to the last, and so on. Okay. Okay, what else do we have? One more important property is that if let's say A transpose A has an eigenpair lambda comma v, lambda comma v is an eigenpair. What do I mean by an eigenpair? I mean lambda is an eigenvalue corresponding to the eigenvector v. Okay. In that case, what will be the eigenpair of A transpose? It will be lambda times A into v. It's very, you can easily see this. Okay. This is an eigenpair. Okay. Let me add a new frame. All right. What else do we have? Uh, yeah. So suppose, what was the last point I wrote here? Fifth point, right? So the sixth point is somewhat related to the fifth point. Let us say A transpose A has an eigenpair lambda comma v with an additional property that the norm of v is 1, which means v is a unit vector, right? In that case, can you find an eigenpair of A transpose which has unit length? That is the question. And in fact, it turns out to be yes. We can take lambda with AV divided by norm of AV. Okay. And it turns out that norm of AV is under root of lambda, which means this is same as lambda comma AV by under root of lambda. Okay. Why? Because this is also something you can easily see that the norm of AV will always be equal to 1. Okay. What else do you need to know? Also, you need to know how to compute eigenvalues. Okay. So given a matrix A, you must know how to compute eigenvalues. And you can use this A minus lambda I determinant equal to 0 and then solve for lambda. What else is there? Yeah, also given a matrix A and eigenvalue lambda, you must be able to compute the eigenvectors corresponding to that eigenvalue. How will you compute? You will have to do A minus lambda I times v equal to 0 and then you have to solve for v. That is how you will compute eigenvectors corresponding to an eigenvalue. Eigenvectors. Okay. These things are prerequisites. You should know all this. Okay. All right. What else do we have? Okay, that is cool. We will continue with what exactly does PCA do, right? Why do we do so? First of all, why do we do PCA? Let's say you have some data set x1 up to xn, right? All of them are, let's say, in RD. Okay. And for some reason you don't want to store all these numbers. You don't want to store capital N into D numbers. That is too much for you. Okay. So what do? You try to use proxies of these data points. Okay. For example, if let us say I have data points like this. These are my original data points. Okay. And someone is suggesting, let's say I am suggesting that hey, don't store all of these. I will only store these points. Okay. So I'm actually bringing all of them down, projecting them onto the x-axis, and I'm saying, hey, I'll store all of these entities. Okay. I'll store the green entities. Okay. And in order to store the green entities, what do I need to store? I just need to store the direction, which is 1 0. 1 0 is this direction. I need to store this direction and I need to store what are the scalars corresponding to these projected data points, right? For example, if my red data point here, if this was 2, 2, and the last one was 10 comma 10, then I have to store, or not 10 comma 10, let me 10 comma let's say 15. In that case, I have to store only 2 here, 10 here, right? Because this green point which I have, this green point is nothing but this green point. This is 2 times 1 0, and this is nothing but 10 times 1 0. So in order to store the proxies, I need to store 1 0, and I also need to store a lot of scalars. How many scalars? The number of data points. So how many data points do I have here? 4, 5, 6, 7, 8, 9, 10. So there are 10 data points. In the original regime, when I'm storing the original data points, I'll have to store 10 into 2, which is 20 numbers or 20 real numbers, right? But as soon as I project them, right, how many do I have to store now? I have to store 10 scalars, right? Plus I have to store this vector, this special vector 1 0, which is 2 numbers, and that is only 12 real numbers. So this is the whole objective about PCA. But now somebody might say, hey, this is not very good because you are moving very far from the red data points. And they will say, instead of projecting along this vector 1 0, let me project along this vector. Oh my god, okay, just a sec. Yeah, this vector, okay. And let us say this vector is 1 1. Okay, so someone might say this is a better choice of projection. Why is this a better choice of projection? Because in this better choice, in the new choice, the distance between the original data points and the new data points, right? So when you project, these projections will lie here, right? It will lie here on the purple line. So the distance between the purple points, let me call them xi hat, and the red points xi, this distance is smaller. That is why the purple choice is a better choice, right? Now what we do in PCA is that we try to algorithmically deduce what is the best choice of projection, or what is the best vector where if we project, we will get the distance as small as possible. By the way, this has a special name. It is called the reconstruction error. So that is so this is an overall intuition about PCA, okay? Second important point about PCA is the reconstruction error. So what is the reconstruction error? It is nothing but the distance or the norm squared between xi hat and xi. Xi hat is the projected xi, or the scalar or the proxy. So you can think of it as projected xi or proxy of xi. Okay, notice that we are not having the same data point, we are having a different data point, right? And the sum of all these, right, over all data points, that is our reconstruction error. Okay, so what is our objective? Our objective is to find that particular v, okay, so that the reconstruction error is minimized. So our objective is to minimize reconstruction error, and it turns out that it is same as maximizing the variance along that vector. Okay, I'm not going into the details about why they are the same and all. It's just an algebraic thing. You can actually you can start with minimizing the reconstruction error, which is 1 by capital N. Okay, let me take a 1 by capital N here just to average it out. I running from 1 to capital N, xi hat minus xi norm square, right? That can be written as 1 by capital N. Instead of xi, instead of xi hat, since I am projecting, I can write it as projection of xi onto v. Okay, let me take v as of now. Minus xi norm square. And it turns out that you can do some manipulation here. It's very straightforward. That it is equal to negative of v transpose of uh, the variance covariance matrix times v. Okay, and what is this? This entity is the variance along v. Okay, but observe that there is a minus sign. Because of the minus sign, we have to maximize the variance along that vector. Okay, and why we do this is because problems become easier in this regime. In the maximizing the variance is relatively straightforward, right? So what are the steps that are included? First, you have a data matrix X, which is of size D cross N. First, what you do, you center it, XC, which is the center data matrix. That is always the first step. Okay, please do not forget to center the matrix. Centered data matrix. What do you do next? You compute the covariance matrix, which is 1 by n. I'm sometimes using capital N and small n, but I hope you are aware that they are essentially the same. Okay, XC transpose, sorry, XC transpose. This is my covariance matrix. What is the second job? So my first job is to compute the covariance matrix. After that, I have to compute largest eigenvalue of C, right? Or you can say k largest eigenvalues of C. What is k here? Let us say we want to project onto a k dimensional subspace. Suppose we want to project onto a k dimensional subspace, and naturally this k will be lesser than small d, right? For example, in this simple example we took, what was d? D is 2. What is k? K is 1. We are trying to project along a line only. Okay, so then we compute the largest eigenvalue or the k largest eigenvalues of C. After this, you have to compute the largest, or you can say the eigenvector corresponding to those eigenvalues. Eigenvectors corresponding to those eigenvalues. Okay, and these are my principal components. In fact, you have to normalize them. Okay, you normalize them, and then whatever you get, they are our principal components. These eigenvectors are the k principal components. Okay, all right, that is cool. Pretty much this is everything about PCA. What else do we have in PCA? Yeah, one quick thing is that uh, yeah, I think this is pretty much it on PCA. Okay, so that is more or less all about PCA. We will move to kernel PCA next. Before that, any question, guys? Okay, I guess no questions. If there are no questions, we will move to kernel PCA. Okay. Is this? Oh, good question. Session was not being recorded. Let me record it. Where is the recording? You're not allowed to record this call. That's what they're saying. Can you see this? I think it's automatically being recorded and it will be shared to you guys. That is what I think. Okay. Anyway, I will record it. Don't worry. Uh, I'll share the recording with you guys. Okay. Let's see. Okay. Let's anyway continue with kernel PCA. So first of all, why kernel PCA? Because we want to capture non-linear relation between the features. To capture non-linear relations between the features. Okay, and this is not just about PCA. For a lot of algorithms, we use the kernels. Kernels are used to capture non-linear relations. Even in deep learning, even in neural networks, you use kernels. Okay, and that is again having the same purpose, which is to capture non-linear relations. Okay, so what do you need to know about kernel PCA? First of all, you have to know that it is actually a trick. Okay, you're moving from a smaller dimensional space r small d to a bigger dimensional space r capital D. How you are moving? You're moving using a function phi. Okay, a function phi. And what do we know this phi? This phi is initially not known to us. Not known to us. Okay, but when it moves, okay, we are not interested in the function phi in itself. We are interested in a modification of that function. What are we interested in? See, once we move from a small space to a bigger space, my new data matrix, what does my new data matrix look like? Phi x. This is what it looks like, right? And what will be the size of this data matrix? See, this data matrix is of form phi of x1, so on, phi of x capital N. And each of them are vectors in R capital D. So the size of this matrix is capital D cross capital N. Capital D cross capital N. Okay. Now what are we interested in? We want the covariance matrix of this entity, which is 1 by n times phi x c minus, not minus, phi x c times phi x c transpose. Okay.
Excuse me, sir.
Yeah, go ahead.
Sir, sorry to interrupt you. I just joined. Sir, are you discussing PYQ or any like?
No, I'm not discussing PYQ. We are doing a revision of all the topics in week 1 to 4.
Sir, okay. Sir, I'm not recording the session.
There is no option to record. So it says recording unavailable. You're not allowed to record this video call. I think I think it is automatically recorded. I'm not sure. Okay, don't worry. I will try to share something. Okay, don't worry. Oh, I think probably the control is with Srinivasan. But let's see. Don't worry, we will figure it out. Okay. So this is my new data matrix. And now what we are interested in? We are interested in this entity, right? This entity. Okay. Now let me write down one more thing. Whatever we call as the kernel matrix, it is this guy, k equal to phi x transpose phi x. So what is the dimension of phi x transpose? It is n cross capital D. And what is the dimension of phi x? It is d cross capital N. So the dimension of k will be capital N cross capital N. Okay, that is the first thing. Secondly, so this is what, this is the kernel matrix. There is another entity called the kernel function. What is the kernel function? The kernel function is a map. So this is small k. Okay, small k. It is a map from Rd cross Rd to R. What does it mean? It means it takes two vectors as input and it outputs a scalar. How does it do it? You give it two vectors xi and xj as input. It will give you phi of xi transpose with phi of xj. Why? What is the relation between kernel matrix and kernel function? Okay, relation between kernel matrix and kernel function. What is the relation? The relation is that you take the kernel matrix and look at the ijth entry. See, it's an n by n matrix. So you can look at the ijth entry. That will be same as the kernel function between xi and xj. And it is easily observable. You can just observe because we are doing phi x transpose phi x, right? So the ijth entry has to be this, right? Okay. So, but this is not the covariance matrix, right? The covariance matrix is something different. There are two differences between this, the kernel matrix and the covariance matrix. What are the two differences? First of all, there is a centering. So there are two differences between kernel matrix and kernel function, or sorry, not kernel function, and the covariance matrix. What are the two differences? Number one is that there is a centering first. There is a centering. So you can observe that there is xc instead of x, right? And what is this xc, by the way? The xc is nothing but, if I write xc as, I can write phi of xc as phi of x minus phi of x bar. What is phi of x bar? Phi of x bar is nothing but a similar matrix where each column is the phi on the x bar or on the average. Okay. So I can also write phi of x bar as sum I times phi x. And then I can again write phi xc transpose as phi x minus sum I times phi x. Now what is this I? This I is nothing but a matrix which is of shape n by n. Okay. The shape of the matrix is n by n. And every entry is 1 by capital N. What is so special about this matrix? If you multiply this matrix on the left, or in fact on the right, in fact particularly on the left of phi x, you will get the average along each column. Okay. That is why, so this entity is same as this entity, right? Okay. So coming back, first difference is that there is a centering. Second difference is that in kernel we are dealing with phi x transpose phi x, but in covariance it is phi x times phi x transpose. So there is a difference in transpose. There is a difference in transpose, or you can say they are transposes of each other. Okay, they are transposes of each other. Okay, they are transposes of each other. Uh, now okay. what can I discuss now? Hmm, okay, there is an idea about kernel centering. Okay, so I think I will discuss that while discussing the method of doing kernel PCA. Yeah, that is enough, I guess. Okay, pardon? Yeah, these are all, this is the entire theory of weak to captured in one page. You can think about it like this. So, yeah, we will discuss few more things about kernel PCA, don't worry. Ah, sure. Okay, so now let me go back to our previous discussion. We observed a few things about A transpose A and A transpose, right? Because if we have idea about uh, any one of them, right? If we have idea about the eigenpair of any one of them, then we can automatically get the eigenpair of the other one, right? That is exactly what we used in, no, that we didn't use exactly that in PCA. We will use that in kernel PCA. Okay. So what is the idea? In order to find the eigenpair of this entity, covariance matrix. So let me write it down. In order to find eigenpair of C, which is equal to 1 by n times phi x, phi xc transpose. What we will do? We will find the eigenpair of k. Okay, what is k? K is equal to not k, kc, where kc is nothing but phi xc times phi xc transpose times phi xc. Now you might be thinking, hey, what is the relation between kc and k, right? It turns out that k, if you expand this, you will get it that kc is nothing but k minus I times k minus k times I plus I k I. This is in fact the formula for centering a kernel matrix. Okay, but now in this entire discussion, observe carefully. We have been discussing about phi and k, right, and their relations. But typically, when we do problems, what is given? We are given k. Let me write it down. We are given k either as a matrix, or we are given this function kxi xj. What are some popular choices? So there are two primary examples of popular kernels or popular choices for k. There are two of them. One is called polynomial kernel and the other one is called an RBF or a Gaussian kernel. What do they look like? So for polynomial kernels, we have that k of xi comma xj is given by xi transpose xj plus some constant c raised to the power p, where p is a natural number, it's 1, 2, 3 and all, and c has to be bigger than or equal to 0. What is the RBF kernel? The RBF kernel is given by k of xi comma xj equals e to the power minus 1 by 2 sigma square norm of xi minus xj whole square, where sigma square is again some positive quantity. Okay, these are some popular choices for k. Okay, so how many choices exist for k? So there are so many choices, right? But the criteria is that the k should be equal to phi transpose phi for some function phi, right? So let me just write, let me take another slide. So the idea is that you cannot take any arbitrary function as k. What is k? K xi comma xj. You cannot take any arbitrary function. It has to be in such a manner that it should be written, or you can say it must be expressible as k xi comma xj equals phi xi transpose phi xj for some phi, or equivalently you can say that k must be equal to phi of x transpose phi of x for some phi. This must happen, but every time somebody gives you a kernel matrix or a kernel function, it is very difficult to find this k. So it turns out that there is a beautiful characterization, right? So before that, whenever you can express this as an inner product of two phi's, you call this a valid kernel, a valid kernel, or sometimes a valid Mercer kernel. Mercer kernel. Mercer is, I think, the name. So if I give you a kernel function, how will you check if it is a valid kernel? So that is the next question. If I give you a kernel matrix, how will you check if it is a valid kernel? So you just have to check two things. First of all, you have to check if it is symmetric. Secondly, you have to check if it is positive semi-definite. Positive semi-definite. Okay. So how will you check if it is positive semi-definite? There are 3 or 4 ways. Okay. I hope you know it already. All right. So that is about validity of kernels. You cannot use any arbitrary function as kernels. You have to use only specific ones. And the popular ones are the polynomial kernel and the RBF kernel. Okay. Fine. There is one more important point where there will be a lot of questions, at least 1 or 2 questions, is that if, okay, in polynomial kernels, there are a lot of numbers, right? One is the small dimension d, one is the degree of the polynomial p, and one is the bigger dimension capital D. So what are these guys? This is small dimension, this is degree of polynomial, and this is the bigger dimension. And these have a very good relation. The relation is that capital D is equal to p plus small d choose d, or equivalently you can write it as p plus small d choose p also. It's the same thing, right? So oftentimes what happens is that you are given the degree of the polynomial and the small dimension, and then you are asked what is the big dimension. Okay. All right. Okay, so here we discussed about finding the K principal components, right? I'm going back to PCA. So what we did in PCA, we had a data matrix, we centered it, and then we took the covariance matrix, we took the largest or k largest eigenvalues, we computed eigenvectors, they turned out to be the principal components, k principal components, right? Okay, cool. Now what happens to a new data point? Okay, so for a new data point, let's say x new, what we do is that we write x new as x new inner product with w1 times w1. Okay, what is w1? So the k principal components, let me call them w1, w2 up to wk. Then this can be written as this plus x new inner product with w2 times w2. I hope you all understand that this is actually the projection onto the span of w1, w2 up to wk, right? Plus and so on up to x new wk times wk, right? Now this is same as and in fact we don't do this, is not equal to the, this is the reconstruction of x new. Okay, this is x new hat. Okay, so this is the projection of x new onto the span of w1 up to wk. Okay, in fact this is the new the new data point that we will consider as a representative of x new. Okay, now same thing I want to do with kernel PCA also. How do I do it? So so for kernel PCA, first thing you have to observe is that we start we already know how to compute kc, right? The centered kernel matrix, right? For kc we will compute the k largest eigenvalues and the corresponding eigenvectors. Okay, let me call them lambda 1 up to lambda k, and let me call these guys v1 up to vk. Okay, now what is my principal components? What are my principal components? Remember, kc is not the covariance matrix, it is the transpose of the covariance matrix, right? So the principal components actually are w1 equal to, observe carefully, it will be phi x times v1 divided by under root of lambda 1. Why did I get this? How did I get this? To understand that, go back to this. See, if A transpose A has eigenpair lambda and V, then A transpose will have eigenpair lambda and AV by under root lambda. This same thing I'm using. Okay. Oh, one mistake is that this has to be XC. Okay, not X phi X. It is XC. Okay. But now we don't know phi. So how will we compute the principal components? Right? In fact, we don't. Okay. Before that, let me also mention that these eigenvectors are all in Rn. Notice this, Rn, not Rd, Rn. Okay. So this V1 is in Rn and phi x is of dimension what? D cross n. So this multiplication is actually possible, right? Now what? Now let me do the previous thing. If I have a new data point x new, how do I compute its representation? It is nothing but, in our original, in the previous one, what did we have? We have x new inner product with w1 times w1, right? Plus and so on, x new inner product with wk, okay, times wk, right? But here we are using kernel PCA, so instead of x new, we will consider phi of x new and phi of x new. This is the only difference. Okay. Observe also that the norm of W1, in fact, the norm of all Wi's, they are equal to 1. Okay. Let me generalize this. This is Wi equal to phi x c Vi by lambda I. Okay. General formula. So this is my new, the projection of the new data point, or you can say the reconstruction or the representation of the new data point. Okay. How is it, but still we don't know phi. How are we going to compute this, right? We don't know phi yet. So the idea is this, you can actually write this as, observe carefully, phi x new transpose. Now instead of W1, I can write phi xc times V1 divided by under root of lambda 1 plus and so on. It will go all the way up to phi x new transpose phi xc vk divided by under root of lambda k. Oh, I missed did I miss? Yeah, I missed this thing. Just a second. Yeah, this is a bracket here. I missed it. Okay, and there is a, and outside this there is another W1. Okay. Let me increase the brightness. Yeah. This is a bracket. That's a WK. Okay. Now what? Now the idea is this, that instead of having, so now what you can do, what you can think about is that consider this multiplication. Okay, this multiplication and this multiplication. This is something which we already know. What is this equal to? This is nothing but k of x new with x1c. What is x1c? The centered x1 data point. Then you have k of x new with x2c and all the way k of x new with x nc. This is this is a vector. You can think about this as a vector, right? Okay. Cool. Mm, what else do we have? Just a second. Yeah, this is fine. I'll not go deeper into this. It's already 1 hour. Okay, but if you have time, you can try expanding this and all. I'll leave it as an exercise or something. But I have seen that lot of there are not many questions that come from this part, so I'm not going into it. Cool. Most questions come from these parts. Okay, kernel validity, centering the kernel. Yeah, these are the two important parts, and this polynomial kernels formula. Okay, cool. Okay. What else can we do? Fine. What do we have next? I think it is estimation. Okay, so let's quickly look into the important parts about estimation. So in the context of estimation, there are two primary things. Uh, One is the maximum likelihood estimation, or it's called MLE, where what we do, we try to maximize the likelihood. Okay. Now, what is the likelihood? The likelihood is actually a function of the parameters given some data points. Let me call all the data points as x bar or some x with a bar below. Okay. How to compute this likelihood? It is either the joint PMF in case of discrete distributions, and it is the joint PDF in case of continuous distribution. I hope everybody knows what is joint PMF and joint PDF. You just have to take the product of the PMFs and the product of the PDFs, right? Second thing is that whenever you want to maximize the likelihood, maximizing L theta is same as maximizing uh, the log of L theta, right? So most of the time you maximize the log of L theta. Okay. Why they are the same? Because log is monotone increasing. Monotone increasing. Okay. And how do you solve for this? You take derivative. So you do dou log L by dou theta, set it equal to 0. You get some value of theta. Then you also do dou 2 log L by dou theta 2. This has to be negative, right? So this is the first order condition. Using this first order condition, you will get a theta. You will call it theta hat ML or something. And then you also check for the second order condition, right? You put in that theta hat ML here in the second order condition and check if it is negative, right? So from the first order condition, you obtain by solving for theta, you obtain theta equal to, let's say, theta hat ML. Then what you do, then you apply theta hat ML here. Okay, so let me write it as theta square and apply theta equals theta hat ML here, and it should be negative. Only then you can be sure that it is actually maximizing and not minimizing. Okay. This is the standard way to solve for maximum likelihood estimates. And this works across distributions, be it discrete, be it continuous, doesn't matter. Okay. Okay, cool. So that is all about maximum likelihood distribution. Let us see if we get time, we will solve some examples also. And anyway, I'll be holding a PYQ session tomorrow morning, so you guys can attend that as well. And I think one PYQ has already been solved by Srinivasan. Okay, so the next idea is that of Bayes estimation. So Bayes estimation is very straightforward actually. People unnecessarily complicate it. The entire idea about Bayes estimation lies in this particular understanding or this particular equation, that the posterior is proportional to the likelihood multiplied with the prior. Now we will go through what these mean one by one. First of all, what is the prior? The prior is, you can think about this as the initial belief about the parameter. Initial, oh my god, what is this? Just a second. Let me just refresh it. Yeah, I think it's back. Cool. So the prior is the initial belief about our parameter. See, in both cases, what we are doing, we are trying to estimate the parameter, right? We don't know what the parameter is. We observe data and then we try to estimate the parameter. In maximum likelihood, we simply maximize the likelihood. In Bayes estimation, we do something a little bit more complicated. We start with saying that, hey, our parameter in itself has a distribution, okay, and we specify that distribution, and that distribution is called the prior. So you can also say that this is the initial belief or distribution about our parameter. What is the likelihood? The likelihood can be thought of as the distribution about the parameter given the data points or given the observations. So given the observed data, what is the distribution of our parameter? That is the likelihood. And what is the posterior? Posterior is nothing but based on our initial belief and the observed data, what is the distribution of our parameter? So based on initial belief and observed data, what is the distribution of our parameter? This is the posterior, and this is it actually. Okay, and we will not consider random priors and random posteriors. Priors are always chosen in a way. Okay, so priors are always chosen conveniently. Priors or prior distributions, okay, are chosen conveniently. What do I mean by conveniently? I mean that when you multiply it with the likelihood, whatever you get should be a very good, nice distribution. So it must have good properties. Okay, it must be a popular distribution. A popular, not, it shouldn't be a popular distribution. Uh, the posterior must be a popular distribution. We typically have priors chosen in a way that the posteriors become a very popular distribution, right? For example, beta. If you choose beta as the prior, and if your likelihood is let's say binomial or Bernoulli, then posterior also turns out to be beta, right? Which is very smooth, which is very good, right? So that is how we always have priors, okay? So some people write the prior as p theta, and the likelihood is nothing but p of theta given x, right? And the posterior is nothing but uh, oh, no, just a second. Likelihood is p of x given theta, and the posterior is nothing but p of theta given x. Okay. Okay, fine. That is one thing. What else do we have? That is pretty much it. This is actually a very small topic. Most of the ideas are can be solved using these techniques. Okay. Okay, what next? Next we have GMM and EM algorithm, right? Let me take a new slide. Gaussian mixture models. Okay. So what are, first of all, what are Gaussian mixture models? The idea of Gaussian mixture models is actually very simple. In fact, you only have to know about its PDF. PDF is not the book wala PDF, it is the probability distribution function. Okay. So the PDF is given by summation of pi j normal distribution x with parameters mu j and sigma j square, where j will run from 1 to capital K, and the sum over of all pi j's must be equal to 1. This is the PDF. Okay. So now you understand why it's called Gaussian mixture, because individually you have Gaussian and then you take a mixture of them, right? Now, okay, first of all, how many parameters are there? You have mu j and sigma j square. How many times? You have k times, so that is 2k, and then you also have pi j, which is k, right? So it's actually how many k? Can anyone tell me how many parameters we have? 2k plus k, right? 3k. There are 3k parameters, that is fine. But how many free parameters do we have? How many free parameters? What do you mean by free parameters? Observe carefully that the summation of pi j is equal to 1. What does it mean? It means if I tell you what is pi 1, if I tell you what is pi 2, and if I tell you what is pi, let's say k minus 1, can I tell you what is pi k? No. Pi k is automatically decided because the sum should add up to k. Sorry, sum should add up to 1. So if you know pi 1 up to pi k minus 1, then pi k is automatically decided, which means pi k is not free. So the number of free parameters is actually 3k minus 1. One of them is not free. Okay. Okay. How do Gaussian mixture models arise though in general? Anyone, any guess? One simple example is that you can think about the quiz happening tomorrow. Tomorrow's quiz, uh, if you if you take the distribution of the marks obtained by students in tomorrow's quiz, you will not get something like a normal distribution. You will probably get something like this. Uh, Probably a lot of data points here, lot of data points here, and you will have some data points here. And individually, it will look something like this. So let's say you have a small normal distribution here. You have another small normal distribution here, maybe a bigger one, and then you have even smaller normal distribution here. It will look something like this. Why does it look something like this? Because there will be students who have studied a lot. There will also be students who did not study a lot, but they simply solved some PYQs. And then there will be another class of students who only studied last night or the previous night study. Right? So there are three classes of students. That is why you might obtain three different kind of clusters, right, in tomorrow's quiz. Now, what is the idea? The idea is that uh, you can observe the marks. You can observe marks of each student. Each student, but you cannot observe or you cannot know what is the whether they have, how much they have studied. So you cannot know how much they have studied, how much they have studied. Okay. All right. So what happens is that we have a hidden variable, right? What is that variable? How much they have studied is a hidden variable. Hidden variable, it is how much they have studied. Because we cannot observe it, right? So it's hidden. Okay. All right. Uh, Now comes, so because there is a hidden variable, it is typically difficult to estimate it in a natural fashion, right? So there is a technique called as EM algorithm which helps us to estimate the parameters. We will discuss what the EM algorithm is now. Okay. First, what you will do, you will initialize. First of all, it's an iterative algorithm. Okay, you will run it over and over again. Okay, it's not like MLE that you maximize something by hand and then you get a closed solution. That is not how it works. It's an iterative algorithm. Okay, like gradient descent and all. Okay. In the first step, you initialize the parameters. So you initialize all the mu j's, all the sigma j squares, and uh, and all the pi j's. Okay, you initialize them randomly. Randomly. What do you do next? Next, you compute these quantities called, let's say, gamma ij. Okay, I think they are using lambda. Just a sec. Lambda ij. Okay, I think in the course lectures they are using lambda, right? So lambda ij is nothing but pi j times normal of xi with mu j and sigma j square divided by summation over k running from 1 to capital K pi k normal distribution xi mu k and sigma k square. Okay, see what are we doing here? Observe carefully. What is this xi? x1, x2 up to xn. These are my observed data points. Okay, then you're calculating these entities lambda ij's. What do you do after that? Once you have lambda ij's, you recompute the values of mu j, sigma j and pi j. How do you recompute it? You say mu j is nothing but, my new mu j is nothing but the average of my data points, but not just a simple average, the weighted average where the weights are lambda ij. Here remember the sum is over I running from 1 to n, that is the sum. See, because you have a j on the left hand side, so on the right hand side also you must have a j. So the I should go out. That's why you're summing over I, right? That is fine. Along with this, you also update sigma j square. How will you update it? You will take again lambda ij and then you will do xi minus mu j whole square divided by summation of lambda ij. Again sum is over I. Okay, sum is over I. Sum is over I. What do you do next? Next you update pi j's. And how do you update pi j's? Pi j's are updated as just 1 by n summation uh, lambda ij. I running from 1 to n. This is how you update the pi j's. And then you repeat. Okay, I wrote 4 here. I don't know why. It's actually 3. So after this, you repeat 2 and 3 until convergence. Okay. So repeat 2 and 3 until convergence can be anything. Okay, you can define convergence as that the difference between two consecutive mu i's are very small, or difference between two consecutive sigma j's are very small, and so on. Okay, there are so many ways to know how to stop. Okay, in fact, you can even say that, hey, I will only run it for 1000 times. Okay, after 1000 times I will stop. So I'll just write repeat 2 3 until convergence. Okay, that is all about the EM algorithm. But now see, one thing you have to understand, there is something very crucial about this guy lambda ij. What does it say? it actually gives you the probability of, so this is the probability of the xi to belong to jth cluster. That is the intuition, or you can say the interpretation of lambda ij. Okay. And look at all these updates. These updates are not something very, arbitrary. For the mean, you are just taking the weighted mean. For the sigma j square, you're just taking the weighted, some difference between squares or the weighted variance, right? And for pi j, you're just adding up the lambda ij's, right? Because what you're doing, you're adding up the probabilities of any point to belong to the cluster, right? Okay. Also observe that if you do summation of lambda ij over both I and j, then you will get 1. Okay. Just note it. Okay. Okay. What else do we have? Uh, okay. I think this is all done. Yeah, this is fine. Cool. Any doubt, guys? Any doubt or any questions? Feel free to ask now. No doubts, is it? What are we in revision session? Yeah, yeah, we are revising. Yeah. No, we revised all weeks from week 1 to week 4. Okay. No, we are not discussing. Yeah, I think I answered these guys. Anything else, guys? Any questions? Any particular questions that you are stuck in? Any PYQ, any PA, GA, any question? Just you can ask now. Anything, guys? Oh, just a second. There is a small kind of an error here. This should be a row matrix. Okay. So this whatever you obtain. Okay. So I just wrote it differently. Just a second. Yeah. So this should be like this: k x new comma xc. Okay. x1c k x new comma xc2 and so on. K x new comma xc. I think the last one is capital N. Right? This is this entity. Okay. Okay. And then you multiply it with v1 and all. Okay. All right. I think rest everything is fine. Anything else, guys? कुछ नहीं है तो बंद कर देता हूँ, है ना? I'll wait for I'll wait till 10:30. If you don't have any doubt, then we'll stop the meeting. Okay, so this is the question that we have. Okay, let's try to solve this. This is a question on a GMM and EM algorithm. Okay. So what does the question say? It says what is the probability that x1 belongs to the first component, right? Now if you go back to here, this is exactly this, right? Probability of xi belonging to the jth cluster. And what is it? It is lambda ij, right? So you have to compute this entire entity. So what do you have to compute here? See, you're talking about the first component. So you have to do this pi1 times normal distribution of x1. Why x1? Because we are looking at the probability of x1 belonging to the first component, right? With what will be the mean and the variance? Mu1 and sigma 1 square, right? Divided by, again, pi1 times normal x1 mu1 comma sigma 1 square plus pi2 times normal x2, not x1 only, with mu2 and sigma 2 square, right? This is what we want to compute, right? But now observe carefully that if I divide this entire thing by pi1 times n of x1 mu1 sigma 1 square, I'll get something like this. I'll get 1 by 1 plus, here I will have pi2 by pi1 first, right? And then what I will have? I will have normal distribution of xi with respect to x1 with respect to mu2 and sigma 2 square divided by normal distribution of x1 with mu1 and sigma 1 square, right? So if you remember the PDF of normal x mu sigma square, this is given by 1 by uh, sigma under root of 2 pi, right? Then you have e to the power minus 1 by 2 sigma square times x minus mu whole square, right? Or let me rewrite it as e to the power minus 1 by 2 x minus mu by sigma whole square, ठीक है? सही से लिखता हूँ, whole square, okay? So in the numerator you will have a 1 by sigma 1 under root of 2 pi. In the denominator also you will have 1 by sigma 2 under root of 2 pi. But now observe that sigma 1 is also 1, sigma 2 is also 1. So what will happen? These entire entity will get cancelled out. What is remaining? We have e to the power minus 1 by 2, okay? x1 is what? x1 is 1. See here, x1 is 1. So 1 minus mu1 is again 1, divided by sigma 1 is also 1 whole square. But this term is 0 because 1 minus 1 is 0, right? And divided by, you have e to the power minus, my bad, just a second. This should be normal of xi with mu2 and sigma 2 square. So this should be 1 minus 3 by 1 square, okay? And in the denominator you will have e to the power minus half 1 minus 1 by 1 whole square. This term is 0, right? So this entire term turns out to be equal to 1 because e to the power 0 is 1. And this entire term turns out to be e to the power minus 1 by 2 times 4, that is minus 2. So what do we, and pi 2 and pi 1 are what? See, pi 1 is 0.5, pi 2 is also 0.5. So these entities will also get cancelled out. So there's a lot of cancellation and ultimately you get 1 by 1 plus e to the power minus 2. This you can compute, okay? Yeah. Any Okay, so there is one more topic that we will discuss, and the topic is clustering and k-means. Okay, clustering and k-means. Okay, first of all, what is clustering and why we do clustering? Okay, uh, so essentially what we do is that we have a data set, right, where you have a lot of data points. Okay, and then you try to cluster them as the name suggests. Okay, you try to say that, hey, each of them are belonging to a particular cluster, right? So let me give you a quick simple example. Let's say you have a data set in R2, okay, where let's say you have income on the x-axis and say you have expenditure on the y-axis, okay, and let's say you have some data points here and you have some data points here, you have some other data points here, and you have some data points here as well, okay. So now because it is 2D, we are able to visualize and see that, hey, okay, there are 4 clusters, but typically in higher dimension we are not able to do this, right? And that is why we apply an algorithmic way to determine the clusters, okay. That is this entire clustering problem, okay. So in this example itself you can observe that, hey, this is someone on the red data points. These are someone who have a lot of income and they also uh, make a lot of expenses. So it's probably Ambani uh, will be in this point, right? And on the other hand, you have these guys who have high income but very low expenditure. So these are all misers, okay. And you have other set of people who have low income and high expenditure. So these are most of the time these are the freshers, okay. So freshers have low income but they spend a lot, okay. And then you also have people who have low income and low expenditure, okay. So that is, for example, me. I have low income and low expenditure, okay. Fine. So now let me define the setup, okay. Let me define the setup. So what is the setup of the clustering problem? The setup is like this. You have x1, x2 and xn, all of these data points, and you also have z1, z2 up to zn, and each of these z1 up to zn, they are some integer among 1 2 up to k. What is k here? K is the number of clusters. Typically when you do machine learning in practice, k, the number of clusters, is a hyperparameter, right? You tune it using something known as the elbow method and all, okay. I'm not going into that now, but the overall idea is that for the purpose of this revision, this session, let us assume that k is known to us, okay. Somebody tells us k, okay, already, and z1 z2, all of these are one of these 1 2 up to k, okay. What we can observe, we can observe xi's. So xi's are all observable, but zi's are not observable. So, or you can say these are unknown and we have to determine them, right? So how to determine zi? That is the next question, right? In fact, the k-means algorithm or the Lloyd's algorithm, it gives us a method to determine these zi's, okay. First of all, it is an iterative algorithm. It is not like a closed form solution. It is an iterative algorithm. And we are assuming that k is given to us. Okay, these two things are there. Now let us look at the algorithm. So you start with randomly initializing the cluster assignments. So also I will call these zi's as cluster assignments or cluster assignments. Why cluster assignments? Because this indicates what is the assignment of a data point, or to which cluster a data point is assigned, okay. So this indicates to which cluster uh, the data point xi is assigned, okay. That is why we'll call it cluster assignments. So what is the Lloyd's algorithm? First of all, what you do is that you randomly initialize initialize z1, z2 up to zn. And since they are randomly initialized, let me put a 0 at the top. z1 0, z2 0 up to zn 0. Okay. This is the first step. Secondly, what you do is that for t in 0, 1, 2 and so on. So this is like a for loop. You can think about it like a for loop. In 2, there are 2 steps. Okay. So this is like a loop. It will keep on running until some convergence happens. Okay. Until convergence. So what happens? First, you do this kind of computation. Mu j t plus 1 is assigned this value. Take the sum of all xi's. Okay. All xi's which belong to the cluster J. So this is the indicator function that the cluster assignment is equal to J, right? And then you take the average of it. That is, you divide by this quantity, right? Notice that the sum is over I running from 1 to capital N, right? So in fact, these mu j's, okay, these mu j's are known as cluster centroids. Why centroids? Because actually you are taking the mean of the data points which are assigned the jth cluster, right? So cluster centroid, or you can say this is the jth cluster centroid. Okay. And what does this t plus 1 denote in the numerator? That denotes that it is in the t plus 1th iteration. Okay. All right. What next? Next what we do is that we reassign each data point to the nearest cluster centroid. Okay. So how do we do that? We say zi of t plus 1 is nothing but argmin of, so you look at the distance between each data point xi and every other cluster centroid which you obtained previously. Okay. And then you take the minimum out of all of that. That is what is happening. Okay. So you can think about this as reassignment of uh, of cluster centroids or clusters, or let me write it like this: reassigning each data point, reassigning each data point to the nearest cluster centroid. Cluster centroid. Okay. Why nearest? See, because we are taking argmin, right? Right. So this is the overall idea about Lloyd's algorithm. This is what the Lloyd's algorithm is. Okay. One more thing I want to mention is that you can actually start with randomly initializing the mu j's also. That is also possible. That algorithm will also be similar. Let me just write it. Let me just make a note of it. Okay. So you can also do this, that initialize cluster centroids, right? Then you do the reassignment, and then you do uh, uh, the centroid computation. Okay. So the centroid computation is this guy. Okay. This guy is the centroid computation. This is also possible, right? And after the centroid computation, again you do reassignment. This is also a possibility. Okay, you can also do this, and when you do it a lot of times, it doesn't make a difference, right? So in the long run, they give the same results. In the long run, they give same results. Okay. All right. What is the objective function? Okay. So what is the objective function here that we are trying to minimize? So the objective function is given as f of uh, x1 up to xn, z1 up to zn. So it's a function of all the xi's and all the zi's. Okay. And it is equal to summation of, you look at xi, the distance from xi and mu j, right? And you only count it if the ith data point is assigned the cluster j, right? So this is one way of saying that you are computing the distance of each point from its assigned cluster mean or cluster centroid. Okay, let me just make a note of it. So this is like distance squared of each point from its assigned cluster centroid. Assigned cluster centroid or cluster mean. Okay, same thing. Okay, one more thing that I want to mention is that this objective function will always reduce after each iteration. So the idea is that if you take f of x1 up to xn along with, let's say, z1 t plus 1, z2 t plus 1 up to zn t plus 1, okay, that is always less than equal to f of x1 up to xn and then z1 t up to zn t. So for each iteration, this objective function will keep on reducing, right? Until whenever it becomes equal, that means that the process has stopped. Okay. One more thing to notice is that when the process stops or when the algorithm terminates, okay, I will mention two things here. First thing is that algorithm will terminate. Algorithm or this algorithm will terminate. It will never go on running. Okay, it will terminate. I think you can see why it is, right? Because there are only a finite possibilities of cluster centroids, right? So, and it's always going down. It's always reducing, right? So it cannot go down infinitely, right? Because there are only finite possibilities. So it will terminate, but it need not terminate to the optimal value. Okay, it need not terminate to optimal value. Okay, it will only terminate to a local optimum, not a global optimum, not global optimum. Okay, that is the idea, right? Okay, cool. So that is all about k-means and the Lloyd's algorithm, right? Uh, what is the algorithm? Uh, what is the objective function? How the objective function changes, and few things about the algorithm itself. Okay. We'll discuss one more concept, that is of k-means plus plus. Okay. So in k-means plus plus, as I mentioned, first of all, we will start with randomly initializing the centroids. Okay. So let me mention it. So what is k-means plus plus? First of all, it is a method of initialization only. So it's a method of smart initialization. Okay. Smart or clever initialization. So what do we want in an initialization? We want that uh, whenever we are, and initialization of what? Initialization of cluster centroids. Okay. Not the cluster assignments, not ZIs. We are initializing mu j's. Okay. That is why I mentioned this, that you can actually do the algorithm in two ways. Either you can start with initializing the centroids, or you can start with initializing the cluster assignments. Okay. So k-means plus plus is a method of smart initialization of cluster centroids, and remaining everything is the same. Okay, remaining everything is same as k-means, normal k-means. Okay, everything is same as k-means. So what is this new thing? Okay, what is this new thing? First of all, what we do is that, so this initialization method, in the initialization method, we want to select k cluster centroids, or cluster means. Okay, how do we do it? First of all, mu1 is chosen randomly or uniformly. Uniformly means each point has the equal probability. Okay, uniformly from x1 up to xn. Okay, but once mu1 is chosen, what happens? We compute something called di. What is di? Di is the distance of xi, each data point from mu1. Then you compute something known as pi. Okay, so let me write it in general. Okay, it's not always the norm, it can be any distance. So let me just write distance. Okay, it can be any distance, it can be Euclidean norm, it can be the square of the Euclidean norm, it can be the Manhattan distance, it can be the square of the Manhattan distance. So many possibilities. Okay, it will be given in the question. So di is the distance between xi and mu j. Sorry, not mu j, mu1. Then what you do, then you compute these entities, which is nothing but di divided by sum of all dj's, where j running from 1 to capital N, right? And observe that this entity will always lie between 0 and 1, so you can think about them as probabilities. Okay, what is the next step? In the next step, you choose mu2 from x1, x2, and so on up to xn, where these data points have probability p1, p2 up to p capital N. Okay, so you can think about this as the PMF, and then you're randomly sampling from it. Okay, now observe that, let's say x2 is chosen as the first centroid, mu1, then p2 will be 0, right? Because it is di by summation of di, and di will be 0, right? Okay, what do you do next? Next you just repeat 2 3 4, right, until all mu i's are chosen. But now you might think, hey, there are what if you have chosen one, or uh, what if you have chosen three centroids, right? Then how do you compute di, right? In that case, you compute di as the minimum of all the distances between xi and, let's say, uh, mu j or mu k, and minimization over k. Okay, so this can be thought of as the distance of distance of xi from the nearest cluster centroid, nearest cluster centroid. Okay, and then what you do, let me write it down as the fifth step. So instead of mu2, it will be, uh, if you have already chosen, let's say, uh, t of them, then this will be mu t plus 1. Okay, or mu t plus 1 if mu1 up to mu t are chosen. Okay, and then what is the fifth step? The fifth step is that repeat 2 3 and 4. Okay, until all k centroids are initialized, or k centroids are chosen. That is the idea. So this is all about k-means plus plus algorithm. Okay. So we have covered clustering and k-means, where we discuss Lloyd's algorithm and a few details about the objective function, how the objective function behaves, termination, and termination need not be to the optimal value. And then we discussed a variant of k-means plus plus, where it's almost the same as k-means, but the initialization method is slightly different, right? Where what we are doing is that, see, the ultimate idea about this initialization method is that we are trying to choose cluster centroids which are very far from each other. Okay, let me just write it down. So the aim is to choose cluster centroids, to start with cluster centroids which are far to each other, which are uh, which are far from each other. Okay, so this is the entire idea.